Hi students, I am Prashant P. Chandran, Assistant Professor, Automobile Engineering Department, SNIT, Adoor. Welcome to my new video. This video, we are covering the portions in our third module, that is forging machines, forging defects, and forging tests. Okay. First of all, forging machines. The first machine is board hammer. That is our forging hammer. You can see the diagram. There are two rollers and a board. A ram is there. The ram contains an upper die, and in the anvil there is a lower die, and the workpiece is placed in between the upper and the lower die, and force is applied to the ram through this roll and board. The upper die and ram are raised by friction rolls gripping the board. After releasing the board, the ram falls under gravity to produce the blow energy. The hammer can strike between 60 to 150 blows per minute depending upon size and capacity of the hammer. The board hammer is an energy restricted machine. The blow energy supplied equals the potential energy due to the weight and the height of the fall. That is, potential energy is equal to mgh. This energy will be delivered to the metal workpiece to produce plastic deformation of the metal. Okay. The second one is forging hammer or drop hammer. This will provide rapid impact blows to the surface of the metal. Dies are in two halves. That is, lower die which is fixed to the anvil, and upper die which moves up and down with the TUP. Energy from a gravity drop is absorbed into the metal, in which the maximum impact is on the metal surface. Okay, dies are expensive because they are being accurately machined from special alloys in order to cope up with the thermal shock. Drop forging is good for mass production of complex shapes. Okay. For example, our spanners, etc., are made by drop forging procedure. Okay. Here the TUP means a weight which is suddenly dropped into the upper die. Okay. That means a sudden impact force is applied on the workpiece metal. Okay. The next one is power hammer or hydraulic type. Power hammer provides greater capacity in which the ram is accelerated on the downstroke by steam or air pressure in addition to gravity. Here a piston is there which can be moved up and down by using pressurized air or steam. Steam or air pressure is also used to raise the ram on the upward stroke also. The total energy supplied to the blow in a power drop hammer is given by W is equal to half mv square plus PH, which is also equal to mg plus PA the whole into h, where m is the mass, v is the velocity of ram at start of deformation, g is the acceleration of gravity, P air or steam pressure acting on ram cylinder on downstroke, A is the area of ram cylinder, H is the height of the ram drop. Okay, it's the power hammer. Here for downward stroke, the steam or pressure air which is pressurized is forced from to the upper side of the piston, and for the upward stroke the air is coming and make contact with the lower side of the piston. Okay, here comparatively the upward stroke moves faster because there is a piston rod which acts which also there in when the air comes at the lower side of the piston. Okay, next one is hydraulic press forging. Here hydraulic oil is used, that is a pressurized fluid is used to move the ram down. Okay, using a hydraulic press or a mechanical press to forge the metal, therefore gives continuous priming at a forming at a slower rate, provide deeper penetration, better properties, more homogeneous, and it is equipment is more expensive. Okay, hydraulic press can give continuous forming at a slow rate, and they provide deeper penetration. More improved properties can be obtained by using hydraulic press forging, and thus the equipment is expensive. Okay. Next one is mechanical press forging. Here there is a crank arrangement. The crank press translates rotary motion to reciprocating motion of the press slide. The ram stroke is shorter than in a hammer or hydraulic press. The presses are rated on the basis of the force developed at the end of the stroke. The blow press is more like squeeze than like the impact of the hammer. Therefore, dies can be less massive and die life is longer than with a hammer. The total energy supplied during the stroke of a press is given by W is equal to half I into omega O square minus omega F square, where I is the moment of inertia of the flywheel, omega is the angular velocity, that is omega O original angular velocity, and omega F angular velocity after deformation. Omega is calculated in radian per second. Okay, you can see the ram and the dice and the workpiece also in the diagram. Both the strokes are there, that is top stroke and bottom stroke, that is upward stroke and downward stroke. Okay. Next one, forging defects. In forging also there are a lot of defects which may occur. Okay. Defects from melting practice such as dirt, slag, blowholes, etc. Ingot defects such as seams, piping, cracks, scales or bad surface and segregation. Defects due to improper heating and cooling like burnt metal, decarburization and flakes, faulty forging design, faulty die design, mismatch in forging, etc. are all the causes of forging defects. Various forging defects are unfilled sections. In this, some sections of the die cavity are not completely filled by the flowing metal. The cause of the defects are improper design of the forging die or forging techniques. Second one is cold shed. This is shown in the diagram. This appears as small cracks at the corners of the forging. This is caused mainly by the improper design of the die, wherein the corner and the fillet radii are small, as a result of which metal does not flow properly into the corner and ends up as a cold shed or fold. This is the reason. Next one is scale pits. This is seen as irregular depositions on the surface of the forging. This is primarily caused because of improper cleaning of the stock used for forging. The oxides and scales gets embedded into the finished forging surface also. When the forging is cleaned by pickling, these are seen as deputations on the forging surface. Fourth one is die shift. This is somewhat similar to that you have studied in our casting. This is caused by the misalignment of the half dies, making the two halves of the forging to be of improper shape. It is also called as mismatch. Flakes. Fifth one is flakes. These are basically ruptures caused by the improper cooling of the large forging. Rapid cooling causes the exterior to cool quickly, causing internal fractures. This can be remedied by following proper cooling practices. Next one is improper grain flow. This is caused by improper design of the die, which makes the flow of the metal to be not in the final intended direction. So the next one is laps. Laps are formed by web buckling during forging. To avoid laps, web thickness should be increased and properly designed. Next one is burnt or overheated metal. This is caused by improper heating of metal at high temperatures for a long time. Okay, these are all the forging defects. Next one is forging tests. There are various tests. Some of them are explained here. First one is the forging test. Metal selection must be considered carefully in forging manufacture. The ability of a metal to experience deformation without failure or cracking is an important characteristic to consider in its selection as a material for a forging process. Commonly used forging tests are upsetting test and hot test. Upsetting test. It involves compressing a cylindrical workpiece between two flat die. This is called upsetting the work. Thus, this test is called upsetting test. Here, the workpiece is compressed by flat open die, reducing the work in a height until crack forms. The amount of reduction can be considered a measurement of forgeability. Upsetting tests can be performed at different temperatures and at different compression speeds. Testing various temperatures and strain rates will help to determine the best conditions for the forging of a particular metal. Hot test. Next one is hot test. Here a round bar is twisted in one direction until material failure occurs. The amount of rotation is taken, a quantitative measurement of metal forgeability. This test is often conducted on a material at several different temperatures. The number of turns that each specimen undergoes before failure is observed. The temperature at which maximum number of turns occurs then becomes the forging temperature for maximum forgeability. For warm forging, temperature ranges from 200 degrees centigrade to 300 degrees centigrade for aluminum alloys and from 550 degrees centigrade to 750 degrees centigrade for steels. Okay. Thank you for watching this video. Have a nice day.